Hello students, welcome to today's physics lesson. In this lesson, we will learn about an important topic in modern physics called blackbody and blackbody radiation. By the end of this lesson, you should be able to explain what a blackbody is and blackbody radiation. Describe how the color of a hot object changes as its temperature increases. Explain why a blackbody is not necessarily black in appearance. Give examples of objects that approximate blackbody behavior and state the 4 important laws associated with thermal radiation. What is a blackbody? A blackbody is an idealized physical body that absorbs all electromagnetic radiation incident on it, regardless of its wavelength, frequency, or angle of incidence. In simple terms, a perfect blackbody is an object that does not reflect or transmit any radiation that falls on it. It absorbs all of it. A blackbody is also a perfect emitter of radiation. Therefore, an ideal blackbody is both a perfect absorber and a perfect emitter of radiation. It is important to understand that a blackbody is an ideal concept. No real object in nature behaves as a perfect blackbody. Let's look at an easy way to understand a blackbody. Imagine a hollow oven with its inside walls coated with the blackest black imaginable. Suppose there is only a very small hole in the oven. When radiation enters through the small hole, it undergoes repeated reflection and absorption inside the cavity. Eventually, almost all the radiation is absorbed. The small hole therefore behaves approximately like a blackbody. This type of arrangement is called a cavity radiator or blackbody cavity. If we hit the cavity, radiation will emerge through the small opening. The radiation emitted depends mainly on the temperature of the cavity. The electromagnetic radiation emitted by a blackbody due to its temperature is called blackbody radiation. In other words, blackbody radiation is the thermal electromagnetic radiation emitted by an ideal blackbody. Remember that all objects above absolute zero temperature emit thermal radiation. You, your chair, your table, the walls of your classroom, the earth and the sun are all continuously emitting thermal radiation. However, at ordinary temperatures, most of this radiation is in the infrared region, which our eyes cannot see. What happens when a body is heated? Have you ever seen a piece of metal being heated until it glows? As its temperature increases, its color may change. It may first appear dull red, then become brighter red or orange. And at still higher temperatures, it can appear yellowish or white. At extremely high temperatures, the visible emission can become bluish white. This change in color is related to the distribution of radiation emitted by the hot object. The important point is, as the temperature of a hot body increases, the intensity and distribution of the radiation it emits changes. The term black body does not mean that the object must always look black. It refers to the object's ability to absorb all incident radiation. For example, an ideal black body at ordinary temperature will emit mainly infrared radiation, which is invisible to our eyes. When the temperature becomes sufficiently high, however, some of the emitted radiation falls within the visible region of the electromagnetic spectrum. It can therefore appear red, orange, yellow, or white as its temperature increases. In simple terms, blackbody describes how an object absorbs and emits radiation, not simply the color that the object appears to have. Black bodies that are strong absorbers at a particular wavelength are also strong emitters at those wavelengths. Similarly, weak absorbers at a particular wavelength are also weak emitters at those wavelengths. This principle is expressed by Kirchhoff's law of thermal radiation. Therefore, good absorbers are good emitters, while poor absorbers are poor emitters at the same wavelength and temperature. No ordinary object is a perfect blackbody, but many objects can approximately behave like blackbodies. Examples include the sun and stars when treated approximately as blackbody radiators, hot furnaces, electric heaters, incandescent lamp filaments, heated metals, the Earth approximately when studying its thermal radiation, and warm-blooded animals. The sun and the stars are not perfect black bodies. However, their radiation can often be approximated by blackbody radiation, which makes the blackbody model extremely useful in physics and astronomy. The Earth also absorbs radiation from the sun and emits thermal radiation, mainly in the infrared region. Studying this radiation helps scientists understand the temperature and energy balance of the Earth. The four laws which explain the principle associated with blackbody and thermal radiation are Kirchhoff's law of thermal radiation. Kirchhoff's law states that at thermal equilibrium, the emissivity and absorptivity of a body are related to the same wavelength and temperature. In simple terms, a good absorber is a good emitter. 2. Stanford-Boltzmann law. The Stanford-Boltzmann law states that the total energy radiated per unit area per unit time by a blackbody is proportional to the fourth power of its absolute temperature. This means that a small increase in temperature can produce a very large increase in the amount of radiation emitted. 3. Wern's displacement law. Wern's displacement law states that the wavelength at which the intensity of a blackbody radiation is maximum is inversely proportional to its absolute temperature. Therefore, as the temperature increases, the wavelength of the maximum emission becomes shorter. This helps explain why the color of a very hot object changes as its temperature increases. 4. Planck's radiation law. Planck's law describes how the intensity of blackbody radiation is distributed over different wavelengths for a particular temperature. Planck's work was very important in the development of quantum theory. An important point to remember: all bodies radiate energy as long as their temperature is above absolute zero. The amount and type of radiation emitted depends mainly on the temperature and the nature of the surface. In summary, a blackbody is an ideal body that absorbs all incident electromagnetic radiation regardless of wavelength or direction. It is also a perfect emitter of radiation. Blackbody radiation is the thermal radiation emitted by a blackbody. A blackbody does not necessarily appear black. The term refers to its ability to absorb radiation. All bodies above absolute zero emit thermal radiation. The four laws associated with thermal radiation are Kirchhoff's law, Boltzmann law, Wern's displacement law, and Planck's radiation law. A quick check. What is a blackbody? What is a blackbody radiation? Does a blackbody have to appear black? Explain. What happens to the radiation emitted by a body when its temperature increases? Name the four laws associated with thermal radiation. Thank you for watching. Keep studying physics, keep asking questions, and remember, physics is not just about memorizing formulas. It is about understanding the world around you.